Yes, so it's a real pleasure to have Max Lee back in MLab after a while, and he's he did bachelor's and master's at Penn, right? Together, all in 4 years, I think, and then and zooming. So Max's work is very interesting. Is at the intersection of looking at unmanned urban aerial vehicles, but in the context of controls, in the context of queuing theory, in the context of privacy, as we'll see today. And so it's a real pleasure to have you back in the lab, Max.
Yeah, thank
And
you.
he's going to talk to us about some of his award-winning paper on routing with privacy in drone package delivery systems.
Okay, well, thank you so much for that kind intro. Well, I'm gonna move this way. Maybe this is a better.
Yeah.
This is a better so I don't block anybody. Yeah, it's really nice to be back at Penn. I don't think I've been here. Well, I was here showing my brother around for college like last summer, but I haven't been really in this building for a while. But yeah, so today I just wanted to start a conversation and discussion about some work that we've been doing related to privacy for drone package delivery systems. So, to kind of start all of this conversation, if the clicker will work, I definitely want to acknowledge my collaborator. So this is work that started at the very last bit of my PhD, advised by Dr. Balakrishnan, and then Jeffrey and Alex have been doing a lot of the work on this, and then along with Karthik, who's now a postdoc at Stanford, Gerard, who graduated from MIT, and he is now at the private industry. So to kind of kick us off, this is the structure that I wanted to go through for today's talk. So just to give you kind of an idea of what I mean when I say privacy, and then kind of quantitatively define it, talk about some case studies of actual drone routes, and then go through some heuristics for routing that we've come up with. So first of all, I think maybe this is the crowd that requires this motivation the least, given how many drones I see in this lab, right? So I think all of y'all are probably aware that there's at least a lot of hype and a lot of money going into advanced air mobility, right? In all of its incarnations, from package delivery to air taxis. Plenty of companies out here, I won't name them all, but they're all trying to offer some sort of delivery service through drones, right? So they're coming. Some people say they're coming next year. Some people say they're coming in 10 years, but drone package deliveries are becoming a thing. But of course, if we want these cool new engineering systems, they usually come with some sort of rules, right? So in particular, the rule that is of interest to us is what's called remote identification, which some of y'all might have heard about. So this is now actually it's codified in the federal regulations. It's going to take effect in late 2023. All drones that are operating beyond line of sight are supposed to have remote ID. And what's critical about the requirements is that remote ID requires drones to publicly broadcast information such as their location and their altitude, right? So keep this in mind. Right? So that we have this system that's basically here to ensure safety, right? It's to do real-time conflict resolution. It's to do counter UAS services and so on. Now, this rule is probably here to stay. And we can sort of get a sense of this because someone actually already tried to sue the FAA about this rule. So Tyler Brennan, he owns, I think, this Ray State quad rotor company. He did not like this remote ID regulations. He said it's a violation of his privacy if they can see where his drones are, and federal agents go capture and blah blah blah. Basically, the DC Circuit judge struck it down, right? So the judge said, no, this system is for safety critical purposes. You don't have a case here. That's essentially what the circuit court says. Now, of course, they could still appeal to the Supreme Court, but in all likelihood, it seems that this remote ID rule is here to stay, and all drones in the future will have to be equipped. So with that in mind, rules is even if they're designed for probably a universally agreed upon reason. So the safety of making sure drones don't crash into each other, drones don't, crash into buildings and so on. There are unintended side effects, right? So in this case, imagine a third-party observer. Have some of y'all maybe heard of Flight Aware or Flight Radar 24? Imagine like a Drone Aware or a Drone Radar 24 in the future. These are all publicly broadcasted remote ID signals, right? So you could just put out some receivers, Wi-Fi, Bluetooth based. They haven't quite decided on what remote ID is actually going to use, but you can imagine a third-party company putting out some receivers around the city and passively just collecting all these trajectories of drone delivery operations, right? And if they can collect these trajectories, if they're clever about it, they could potentially deduce who ordered what from whom, right? So imagine these days, if I, order some fries on Grubhub or Uber Eats, and my delivery car has this giant balloon attached to it, and the balloon says, this is Max Lee's fries, right? It is essentially equivalent to kind of this situation, if that's how you want to think about it. So why is this a situation we might care about? Well, imagine that you as a customer, maybe you have a medical condition, maybe you have a particular dietary restriction, maybe you have some sort of cultural adherence, and that's private information to you, right? But your order and your purchase history could tell somebody quite a bit about some characteristics that you have. The example that we always like to use is right now you could order from the mail erectile dysfunction medication, right? That's probably not, that may not be a symptom, may not be a illness that people want out there publicly. Now imagine if you're able to get door-to-door delivery of this medication, and a third party can see that you have this drone coming every month from this warehouse that's known to carry a certain class of drugs, right? And also, so in the extreme case, right? So you can imagine, for example, things like birth control and so on. This could actually pose more than just a loss of privacy, right? This could actually become a physical risk as well. And then, of course, I think nowadays there's been a much more heavy focus on privacy in all realms, right? Digital privacy, location privacy, et cetera. So that's on the customer side, but the companies do care too. So let me give you this example. Suppose you have Walmart and Target. They both offer drone package delivery from their warehouses. You could say, that's fine. It's from a warehouse. You don't know what you bought from the warehouse, right? You don't know. It's a big box store. You don't know exactly what items you got. So maybe this part is not as relevant. But now imagine Walmart services a subset of the population through its drone delivery service. Target services a subset of the population. Let's say Target pays some money to the third-party observer and asks, where are all the customers that are only serviced by Walmart? And now Target could use that information and target those customers and say, hey, we have drone package delivery services too, right? So potentially rival vendors could identify customers to do targeted advertising. And this, of course, can pose loss of competitive advantages and unwanted targeted advertising for the individuals themselves. And of course, vendors want to be cognizant of what consumers care about as well. So in this case, if consumers don't want their stuff revealed, then vendors, especially if they're willing to pay $1 or $2 extra for it, right, to protect privacy, vendors would be interested in that as well. And then the last part here is sort of interesting. This actually we didn't think about until later on. Imagine you're a high net worth individual and you like to get the latest Apple products or the latest jewelries and whatnot. And now if you have drone delivery from those locations, you could have certain socioeconomic statuses revealed just through your drone trajectories as well. So the problem that we're trying to tackle here is that the identification problem of who ordered what from whom from observing trajectories, and how can we, one, first define it, because I don't even know how to define this problem, this privacy risk at the moment, and two, how do we mitigate it, right? So traditional ways of mitigation, you add some random noise to the observed trajectory, But then that defeats the purpose of the remote identification system in general, right? Because then if you're adding noise, you can't do conflict resolution now, you can't do counter UAS operations and so on. So how do we try to protect privacy, reduce privacy without adding noise? Well, first we got to define privacy first. So let's jump right into that part. So to do this, I've just set up some notations. So I'll use this rather simple example. Let's suppose we have 3 customers. So little n is the number of customers, and they are located at 3 addresses, A1, A2, and A3. We also have 3 vendors, let's say little m vendors, and big V contains the set of all vendors. So down here, these 3 are the vendors, right? Selling an apple, a ball, and a pen. And these 3 are the customers, one who wants an apple, this person wants a ball, and this person wants a pen. So this is the toy setup that we'll use to kind of introduce the notion of this privacy risk. So imagine you're the drone fleet operator, right? And you see that these customers ordered, an apple, a ball, and a pen. What does the drone trajectory look like to you, right? You're internal to the system, so you know everything that's going on. So what you would see is that you would see a drone, let's say it picks up an apple, right? And then the drone goes to vendor V2, maybe it picks up a ball. And then, at address A2 for the person who wanted the ball, it would drop off the ball. And then it would pick up the pen from vendor V3. And then it would complete this route by dropping off, the pen at the person who wanted the pen and the apple at the customer who wanted the apple. Right, simple in terms of a delivery route. But now put yourself into the shoes of the third-party observer, right? So what would they see? So this is the actual route, right? This is the actual sequence of pickups and drop-offs. What would the third party see? Well, the third party knows what these vendors are, right? That's public information, right? So you know that one's an apple vendor, a ball vendor, and a pen vendor. So the first 2 observations are exactly the same, right? You see and you know that a ball and an apple was picked up. But at the next address, you can observe that something was dropped off, but you don't necessarily know what it is, right? And you don't know what's on board either, right? You don't know what's remaining on board. At the next stop, you pick up a pen and this unknown item, right? And then at the last 2 addresses, you also observe a drop off, but you don't quite know what that item is. And you don't know what the last item is that was dropped off either, right? So this is from the, let me go back real quick. This is what the third party sees, right? So if we wanted to come up with a model of how the third party might try to deduce what these are, what might be like the simplest model we can think of? The simplest model might just be something based on conditional probabilities, right? So the thought process of such a third party might go as follows. So observe this ball pickup, and then they observe an apple pickup, and then they observe a ball pickup, and then they observe a drop off, and they can construct the empirical distribution of what item was dropped off there at what probability, right? So, you know a priori that there was a ball and an apple. So, my best ability to guess is that, 50% of the times, maybe the ball was dropped, the other 50%, maybe the apple was dropped. So you can construct this discrete distribution. This discrete distribution that's specific to this address and has mass on the individual items, right? Now at this next point, because we now have an unknown item and a pen, we can construct another distribution, right? You can write out your conditional probabilities, etc. And trust me on this. These are the probabilities that you'll get. And then similarly for the last one, it turns out that the distribution for these 2 are actually identical. In the paper, there's an algorithm for if you give me a route, if you give me a sequence of vendors and customers, the algorithm computes all of these distributions in linear time. So it's actually it's a pretty simple algorithm in some sense, right? It just needs to go through the sequence once. So, and then as a reminder, right? So in actuality, a ball was dropped off here, right? So the realization was this this item was dropped off, and then over here a pen was dropped off and an apple was dropped off. So now that we have these empirical distributions, well, I guess they're not empirical. Now that we have these discrete distributions, we can use these to try to define our privacy risk. And how we do that is, so I'm just writing out for the 3 customers. These are each customer A of I's probability distribution of what item was dropped off. And so this is just saying what I said in slightly more formally, right? So each distribution, you can think of it as a map from the set of vendors to some probability, right? Specific to each customer A of I. Then the privacy risk for any individual. So the privacy risk for an individual is just the mass located at the correct item, right? So here an apple was actually dropped off, and there's a 1/4 chance of guessing that correctly, right? So the privacy risk to this individual, I'm going to weigh it as 1/4. For this individual, they received a ball, which had a 1/2 probability, right? So for this individual, I'm going to say that the privacy risk is 1/2. Obviously, doing it this way, the closer to 1 it is, the less private it is, right? And the closer to 0 it is, the more private it is. You're less able to guess. And then from this definition, we can also construct some other stuff, right? So if I give you an entire route, you can of course tell me what is the individual with the worst case privacy risk associated, right? Yes, sorry.
Why do we define privacy risk as the probability that the correct item, the probability of the correct item being, discovered? Why not define it as the maximum possible probability, or the maximum probability over all of the vendors for a given address?
Yeah, so you can so that's almost like a dual way of looking at it, right? So you can certainly look at it from the vendor's perspective, right? So at the very end, when I talk about a privacy-centric vehicle routing problem, you can certainly try to write this privacy risk from the complement perspective in order to bake it into a VRP, right? But for this, this is thinking from the perspective of the customer, right? So the customer knows they got an apple. They want to minimize the chance of someone guessing that they got an apple, which is why we decided to define it in this way.
Isn't someone incorrectly guessing what you have just as bad, right? So like the first customer, the highest probability outcome is that they got a pen, not an apple, right?
Yes.
And you don't want to be mistaken for someone who buys pens. That would be ridiculous, right?
So I think that's a great point. So, especially, so now I think you're getting at a good question, which is what's the threat model, right? If we have a sparse set of vendors and customers, then any privacy mitigation is probably not very useful, because if you know what happened to one person, you can instantly say what happened to the other one, right? When you have more and more, it's true that, then maybe any individual items that wasn't the item you ordered is less important, but the item that you actually ordered would still be important, right? But that's, I think you make a great point in saying that when it's a sparser set, then potentially guessing incorrectly is also intriguing. Right? Thank you. Any other questions so far? I guess this is kind of like one of the main slides because it's defining all the stuff. Cool. Okay, so we can of course also define an average privacy. So just as an example, right? The maximum privacy risk across this particular route is 1/2. And then we can of course define some average privacy risk, right? Which is just looking at the privacy risk of all the individuals, summing it and dividing by the number of individuals. So what's the average privacy risk? So in this case, it's something like I can't do this math quick. 512. So we can define these 3 measures, and now we're kind of in business, right? We can now start trying to apply this and look at trade-offs between privacy and routing efficiency and so on and so forth. So let's walk through this particular metric a little bit more. So how could we actually do better, right? So given a routing, and I'm telling you, you can't inject noise into the trajectory. So you can't say, I don't know what happened to this drone, it's somewhere in this ball. So given that you're not allowed to inject noise, let me propose this first route here which I'm gonna label as blatantly unprivate. So in this route, if you observe a pickup at V1 and a drop off at A2 and a pickup at V2 and a drop off at A2, you can guess with 100% certainty what happens in this route, right? So in this case, the privacy actually for every individual is 1, right? So you have a 100% chance of guessing what happened in this particular routing. But if you just tweak your routing a little bit, and by tweak, I mean, what if you just randomize the order that you went within your vendors, right? And then you went and dropped off these 2 items, right? So what if, let's assume your drone has enough capacity and it can hold 2 items. And let's say you go to these 2 vendors first. So you pick 2 up and then you drop off 1, drop another 1 off. What's your privacy risk now? Well, it's 1/2, right? You only have a 1/2 chance of doing this. And of course, in general, you could think about routings like this, picking up as many as n items, right? And then dropping off n items, then at best, your privacy risk here is 1 over n in this case. One thing that I will say real quick, obviously, at some point your drone capacity comes into play, right? You can't, obviously you can get 0 privacy if you can hold infinite stuff, but at some point your capacity comes in. So I wanted to demonstrate real quick via a very simple geographical example that there can be really, really unintuitive trade-offs between efficiency, which we define as how long it takes for you to receive the package, so your wait time, the customer wait time, and the privacy. So here's the geography. Okay, it's a 1 by 1 square of land. All right. But so these houses are all located 1 apart, and of course these houses are located root 2 apart, right? These 2 and these 2 are located root 2 apart. Again, the math is the very simple math is in the paper. It's just compute the wait times for everybody. Yes.
Is the wait time defined by the start or the order pickup to order delivery, or start of scenario?
Order pickup and order delivery. So for example, the wait time for A1 is 1.
Yeah.
Right. Yeah. Actually, no. Sorry. It's the beginning of the route. My bad. It's
Okay.
Yeah. Sorry. You're right, because otherwise this would not be 2.6. Yeah.
Right.
Yes. Yeah. It's the start of the sequence. Right? Because we assume that you place your order kind of. Yeah. So, although there is an interesting question of dynamic order ring, but anyways, we didn't do that. So this is the super simple geography, right? It's a 1 by 1 unit square. In here, if I give you this routing, V1, A1, V2, A2, the privacy risk is 1, and the average wait time is 2.6 minutes, right? If I just switch up the routing a little bit, so let's say now I do V1, V2, A1, A2, interestingly, the wait time goes down and the privacy risk goes down. So you kind of got both, like you got a win-win situation here, right? Now, let me give you another, so here you can have privacy and efficiency, which is kind of counterintuitive. On the other hand, if I just permute these 2, so same unit square, different geography, you can think of it, right? Because I switched A2 and V2 here. So in this case, if I do a routing like V1, A1, V2, A2, I get privacy risk of 1 and an average wait time of 2 minutes. And if I try to do better, I see that my average wait time actually increases, but my privacy risk decreases, right? So in this case, it turns out there's more of a trade-off situation. There's some sort of Pareto frontier going on here. So this will hint to you already that the moment you bring in geography, things become complicated. And the most correct way of looking at this is you should really define a privacy risk you want to achieve, and then solve a vehicle routing problem that minimizes the efficiency subject to that privacy risk, right? And I think most of y'all know vehicle routing problem, NP hard, as the vanilla formulation, right? Without adding any of this privacy stuff in, right? Anyway, so keep this simpler situation in mind. Basically, geography can do a lot of things to this. Before I talk a little bit more about geography, I wanted to just kind of, make rigorous some intuitions that I had been talking about before. Obviously, if your drone has a limited capacity C, so you can only pick up C equals 1 package or C equals 2 packages, then the worst case privacy risk is lower bounded by 1 over N or 1 over C, right? So you're either lower bounded by, if you do complete aggregation and you can hold all in packages, you can get 1 over N privacy. But if you're limited by your capacity, and if your capacity is 1, for example, then this becomes immediately 1, right? So your worst privacy risk is no better than 1, right? So that's a blatantly unprivate route here. And you can sort of, so for each of these different colored and shaped curves, it's different privacies, it's different capacities. So this is a drone that can only hold 1 package. Then even if you increase the number of orders, you can't really do better than 1 in terms of privacy risk. And you get this sort of diminishing returns as you add more capacity to your drone, or I guess as you dispatch a bigger and bigger drone. Yeah.
So I'm noticing that the capacity 2 drone, so the first one's what we expect, the next one with 2 orders, that's also what we expect, but then it drops below 1 over C.
Yes. So this is the worst case, right?
Oh,
and I'm plotting average privacy risk. Sorry about that. Yeah, I should have. Yeah, this is average privacy risk. Okay. Yes, you're correct. So if I do the worst case, it'll be a boring plot, right? Right. It'll be exactly this, right? Or it'll be lower bound. It'll be lower bounded by exactly that. But the average privacy can. We don't have a closed form for that. Okay. Yeah.
And is this average privacy like assuming that we're seeking to minimize the average?
Correct. Okay. Yes, that's right. This is the minimal average privacy. And now you might ask how we actually got that minimal route. We did it by brute enumeration, which is why we wanted to do the VRP, right? So I'll talk a little bit. I'll talk a little bit about that later. So one solution that one could think about for this finite capacity issue that we proposed in the paper, but we didn't really do much with it, is imagine this situation, right? You have a capacity 1 drone and it picks up from vendor 1 and it drops off at A1. The privacy risk is 1, right? So there's no privacy here. Now imagine, what if we could stop at a vendor, stop there, but not actually pick anything up, right? So think of it as a little decoy vendor. So you could actually provision some services, right? Maybe you could use it for some charging or something. Right? So here we've actually artificially dropped our privacy risk to 1/2, right? Assuming that your decoy vendor, when you do the decoy, it's like the third-party observer cannot tell if you just stop there or if you stop there to pick up a package or to charge, right? Assuming they don't have cameras everywhere. Yes.
So, even when they're stopping at the vendors, they can see whatever they're picking up, right? The third party.
The third party only knows what they're picking up because they know the vendor, right? So yeah, they're like, okay, there's a McDonald's there. If they stop there, I think they picked up a McDonald's, right? So here, this could be, a I don't know, Target, right? McDonald's. So it started from here, so you assume it got McDonald's. Then you see a stop here. As a third party, you would assume it picked up the Target package, right? But what is the biggest trade-off if you do this? The biggest trade-off is efficiency, right? Because now you're doing this extra routing, right? Because think of the case, the hypothetical case where you stop at infinite numbers of fake vendors. Of course, you can do that with the capacity of 1. That's fine, but that would make your routing infinitely inefficient, right? So we proposed this decoy vendor idea. We didn't do too much with it, but and in fact, there's some interesting questions of this. What kind of prices should be charged to offer this kind of service, right? So there's actually some interesting market design questions here, but we didn't really look into it. What we did do is to just say, okay, well, if you have, let's say, ND decoy vendors, then of course, I think pretty intuitively you can add this to you can deflate your lower bound a little bit, right? So whereas before, even with capacity 1, we could do no better than privacy risk of 1. Now we can actually depress this entire curve, right? And again, it's that similar-ish case of diminishing returns as you add more decoy vendors and as you add more drone capacities. Okay, so now let's go back to geography. And I'm,
if you,
oh,
if you
yes.
have these decoy vendors, then,
Yeah.
I mean, the drone's most precious resource is the battery capacity.
Yes.
And then that's like you're hitting that resource the hardest.
That's right. So that's why we were thinking that a good model would be you contract out as a decoy vendor and you provision some charging service, right? So that when you are stopped there, you at least can charge. But again, this still increases your routing and increases this person's wait time, right? That you cannot do much about. Yes.
So the question when it comes to the next slide in the average plots, what's the geography? Like, what's the topology of these?
The topology is infinitely close points.
Okay.
So in these, yes, that's a great question. So in any of these analyses of the privacy only, we pretend that it is, you can either think of it as either infinitely close vendors and customers, or you can think of it as infinitely fast drones, right? So that's a great question, because that's exactly why we were like, this is kind of boring. We actually want to do some real life stuff. This is good to get an intuition of how, you know, capacities, number of decoy vendors, blah, 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 could affect your privacy risk. The curves do not look like this in the real world, right? Which is what I will show now. Okay, so geography. So, you know, flashing back to this simple, you know, 1 by 1 unit square case, right? We see that geography can really boggle the mind a little bit in terms of what it does to privacy and efficiency. So what we did was we set up this the following case study. So we looked at the Boston metro area, and we looked at 6 vendors and 6 customers. All right, and we did kind of a sensitivity analysis, if you want to call it that, with the capacity. So we checked capacities 1 through 6. We didn't do decoy vendors, and we assume some, you know, of course, you can change both of these parameters if you want to, right? This is just to give us a way to actually compute the average wait times, right? So we assume some drone speed, and we assume some time for the stops. You can customize all of this, right? You can customize custom wait times at stops. You can customize, you know, the actual kinematics in here for the speed, so on. Right? We were just trying to get a simple model together. So let me show you one geography that we use. So this geography, it had the vendors all kind of clustered around in downtown Boston, and it had the deliveries all kind of clustered around the MIT campus area. And what we did was, there are 720 possible routes, right? And then within each route, you can have multiple permutations, right? So just, you know, combinatorics here. Here you're seeing a scatter point of, for each route and a given capacity, what is the average privacy risk and what is the average wait time, right? So that's what we're plotting on this plot. Obviously, as you go down here, you're more efficient, and as you go to the left here, you're more private, right? So we can think about looking at the Pareto fronts, right, for each capacity. So let me just clean this up a little bit, right? So for each capacity, all of the other points with a route using that capacity lies strictly to the right and up of these Pareto fronts. So these are, you know, this is the points where you cannot unilaterally do better in both privacy and wait time for a given capacity.
Out of curiosity, does this plot look similar if you look at max privacy risk versus average?
That's a good question. So it's, I think we did do that.
Because, you know, I'm imagining scenarios where you could, you know, minimize average privacy at the cost of one customer.
Yes, yeah. So so you're getting at a sense of fairness there, right? Yeah. So I think we generated those plots, but I truly cannot remember them. But you can certainly look at max privacy. Yeah, so you could look at max privacy risk, and the trade-off there between those Pareto fronts and this one would give you that connotation of, you know, are you screwing over one person in order to minimize in order to minimize others, right? So to kind of build our intuition a little bit more, let's just look at one of these Pareto fronts, right, for the capacity equals 3 scenario. So a point that's down here, this is the point that is most efficient, right? It's the most efficient point, but it's the least private on the Pareto front, right? So what you're going to see now is going to be an animation of how the drone is actually going to, how this route looks like. So what you'll see that the drone tries to, pick up a couple, then go over there, drop off a couple, come back, take up a couple, go there, drop off a couple. It's essentially trying to minimize the amount of times it needs to go across the river, right? Because this is the most efficient solution, least wait time solution. So it's trying to minimize this back and forth. So this route has an average privacy risk of 0.33, and it has a wait time of 13 minutes. So you can try to keep these numbers in your head. I'll also show them again with the full comparison. But basically, this is not good in terms of the bridle front. This is great in terms of the efficiency. So if we zoom up to the other point up here, right? So now this point is the most private, right? But it's the most private, but it's the least efficient, right? So let's see what the drone tries to do in this case. So in this case, it actually does many, many zigzagging trips back and forth across the river. And the intuition here is that it's trying to keep its cargo as full as you can to get this privacy increase by aggregation, right? So it's picking up two, going there, dropping off, going back, picking up one, going there, dropping off, right? But this is extremely inefficient because now you're getting these multiple trips zigzagging across the river, right? So this is very inefficient routing wise. So yeah, so here the privacy risk, you can get a reduction, right? So it drops from about 30% to 20%, right? But for a 7-minute increase in the average wait time. The last point that we'll look at is something kind of, a hybrid solution of both, right? So in this case, this is sort of, shall we say, like it's not biasing towards either privacy nor efficiency. And it's a little hard to tell, but it sort of has some characteristics of both routings in here. So, it does try to keep it full, but it also tries to minimize the number of back and forth that it does. And in terms of the risk, so it's sort of between 0.33 and 0.23, and it's between, 13 minutes and 20 minutes, right? So just as a visual comparison between these three, right? This is the most efficient, this is the most private, and this is something kind of in between. Instantly, you should be thinking about what happens if I change the topology of the customer and vendor set, right? So we also, I won't spend too much time, but we also looked at different, so this is, we called it 2 clusters as the geography. We also looked at sort of so just some summarizing remarks for this geography. If you have bigger drones, you can actually move the Pareto in this diagonal direction, right? So you can improve in both efficiency and privacy. And that's because you could either, do your aggregation and then go there and drop everything off, or you can pick everything up, try to keep yourself as stuffed as you can, and then drop if you're worried about privacy risk. So you can get this unilateral improvement in both privacy and efficiency. So we also tried a hub and spoke topology. So where, the vendors are all kind of in the MIT campus, and then the addresses are kind of, in a spoke pattern throughout. And again, we discussed this a bit more in the paper, but for time, and I also want to leave some time for discussions, I won't go too deep into this. But essentially, interestingly, you see that you can actually improve privacy in this case, but you can't really improve efficiency with more capacity here. So this is probably due to just the measures between the vendors are so much smaller in magnitude compared to the measure between a vendor and a customer. And we looked at a couple of other topologies. We looked at a uniform topology here, where everything's just kind of spread out. And here we see that up to some point, you can only get better privacy by trading off average wait time, right? So the curves are all kind of stacked in this really nice, well, maybe not nice, but really, consolidated Pareto front here. And then we tried one more. Oh, okay. Well, we did try one more, which was sort of this. We tried this linear topology, which all the vendors were here and all the customers were here, and those results were in the paper. I don't really remember them, but anyway, we did try one more topology. So I think the biggest takeaway, at least for me, for these geographic case studies, is that it matters, right? Geography here matters a ton, right? So if you know your vendors and your addresses, you need to kind of solve a unique instance of this problem, right, in the real world. So now the last thing that I'll talk about for the last kind of 5-ish minutes is a heuristic. So again, I think I previewed this. How did I generate these Pareto fronts? Or I should say, how did Jeffrey generate these Pareto fronts? He enumerated brute force enumeration, right? Which of course, if I gave him more than 10, 11 vendors, it would take 2 or 3 hours, right? I think this probably took like 8 or 9 minutes, right? But it's factorial in the complexity in this, right? So this is bad, right? This is, we can't, I mean, if Amazon, let's say, wants to do some privacy-centric thing, they're delivering what, thousands of packages for a route, right? You wouldn't be able to do this, right? So because we didn't want to get into the VRP at first, we looked at a couple of heuristics that actually gave relatively good empirical performance. So I'll just step through a couple of them here. And again, you know, the reasons for doing these heuristics is we saw how geography complicates things. And we know that if we wanted to find the absolute optimal route in terms of efficiency, it's the, you know, it's the more general version of the TSP, right? And this is not even considering, you know, some constraint or objective for minimizing privacy, which is probably not a linear constraint or objective, right? Or maybe it is. We're working on that right now in this formulation. So here we could at least give you a way to plan a route that has a specified routing guarantee. So for every one of my heuristics, you can actually write down the average and max and average and worst case privacy in a closed form. So you could say, okay, I know this isn't the best. I know it may not lie on the Pareto, but at least if I wanted to hit a certain privacy risk, I could do it with this route. I don't have to hand design a route, check it, hand design it again, check it, right? I don't need to do this enumeration. I can at least give you some heuristics to guide this planning. So in this case, in terms of the heuristics, it can really you know, cut down on the number of just brute force enumeration that you'd have to do. So I'll kind of introduce the heuristics kind of qualitatively, and then I'll show you the privacy guarantees on them. So the first heuristic we have created was this thing called a KL split. And the intuition here is that, you know, if I'm capacity limited in a lot of these situations, what if I'm able to split my order into a K partition and an L partition, so that now instead of being lower, instead of only being able to do as well as, you know, C or something, you could do your capacity, instead of that 1/C term in the max, now you have a 1/max of K comma L, right? So just splitting your route into more manageable chunks so that your capacity is not the limiting factor. What this looks like in practice is you go visit the first K vendors. Of course, K must be less than or equal to C, right? And then you go drop off your K items. Then you visit the L, you know, you visit the K plus 1 through K plus L vendors, and then you go drop off these packages, right? Again, you know, K plus L is equal to the number of total orders. And here, if you do have a drone that has decent capacity, you can get more bang for your buck out of that capacity by partitioning it in this way. So that's sort of the intuition with the KL split. Another heuristic is called the K reversal, which is also similar in terms of the philosophy. So we're really trying to get as much out of the capacity as we can. So what we do in this case is we actually force the drone to go visit, you know, the first vendor and then the last set of vendors, drop off as appropriate, right? And then hit up the last K, right? And then drop off as appropriate on the last K, right? So now what you've done here is, well, first, you know, of course, the relationship between the number of packages and this K, where that's part that you're using to partition, it has to be at least greater than 2K. And here, again, you can actually reduce privacy risk, although usually these K reversal heuristic routings tend to have tend to be worse in terms of efficiency. Yes.
Why does N have to be greater than 2K? If K is less than n, k is less than n is less. Is k, if k is both less than n and c, you should be okay, right? Like, why does n have to be greater than 2k?
So n has, so first of all, c has to be also, so your c is kind of a floating parameter here in this case, right? So because what you're doing here is that you need to hold at least 2k things in your cargo belt, right? Yeah, because
Wait,
so you're looking at, you're first getting the first 1 through k, right? And then you're getting the last, like what
oh, I see. Okay.
yeah, you're getting what's remaining, right? And then you're delivering to the first set of 1 through k customers before hitting up the last sorry,
Got it, okay.
not the last after the gray, the grays, right?
Okay, that makes sense.
So this, you can think of this as the KL split, but for privacy and not efficiency, right? And then you have my favorite, which is called C stuffing. And what C stuffing is it's that it's basically you want to keep the drone as full as you can, right? So you have some capacity C, and you want to keep the number of items as close to C as possible. So what you're going to do is you're going to visit up to your capacity, right? Then you're going to deliver 1 item. You're going to visit one other vendor. You're going to deliver 1 item, and you repeat this process back and forth, right? You keep repeating it until it terminates at some point, right? And the intuition here, and then you have to do a kind of a massive drop off at the end when you have no more vendors to visit. So the intuition here is, so actually, we actually saw that empirically. You could probably prove this. I don't know how, but empirically, this is optimal in privacy. So you will always get, so for a C stuffing routing, you'll always get something that's on the rightmost side of your Pareto frontier, right? It's not necessarily the most efficient, right? But the point here is trying to maximize is trying to minimize privacy risk. Okay, so if we apply these to our case study, so if we go back to the 2 cluster case, right? So now I'm going to actually plot what you get with the split, the reversal, and the stuffing. It looks super messy, so I'm going to get rid of some things first. It still looks kind of messy because there's actually a couple of equivalent in terms of privacy or in terms of efficiency routings, right? So I'm just going to plot one example just so that we can see where these solutions lie, right? And of course, none of these heuristics should ever be on the left or below the Pareto, right? Because we can only do as well as Pareto. So at least for the 2 cluster case, a lot of these seem to actually lie on the Pareto curve, although you can't really control where they lie, right? So if you look at a lot of the stuffings, as I kind of mentioned, these stuffings are all privacy optimal, right? But not necessarily efficiency optimal. Yeah, so this is for the 2 cluster, and some things that we see here are that stuffings again is private, but they're extremely inefficient, which makes sense, right? Because you're trying to keep it full, so you might be zooming back and forth. Splitting it gives you actually pretty efficient solution. So these split heuristics tend to be on the bottom of these Pareto fronts, and stuffing you kind of get sort of something in between the 2. Sometimes it doesn't do as well in terms of the efficiency. But of course, the behavior of these heuristics are going to change depending on the topology of your layouts, right? So in this case, again, I think stuffing is the one that is pretty consistent, right? You always see it consistently very private, but also consistently quite inefficient. And you see that here in the uniform case as well, in terms of the stuffing heuristic, and as well as in the, oh, nope, okay, well, that was the last one. Again, there was one more heuristic that was in the paper, but I guess I took it out here for time. I won't go through the derivations for this, but this is just to show that for the KL split, the K reversal, and the C stuffing, you can compute exactly what the individual privacy risk, the worst case privacy risk, and the average privacy risk. Okay, so takeaways, they work well, they save computation, but you don't have any guarantees on exactly what they're going to do. what I want to end with is just first, what did we talk about today? You know, drone private delivery, they're coming, privacy risk, remote ID, right? These are sort of secondary externalities that may not have been, I mean, they're definitely not intended, right? They're not like remote ID was not intended for there to be a privacy loss, but here we are. We talked about how we propose a way to at least quantify this privacy risk given a route, right? We looked at how this privacy risk is affected by parameters like capacity, number of orders, and dummy vendor, decoy vendors, and so on. We looked at this trade-off when you bring in geography, right? This trade-off between efficiency and privacy. We looked at, a couple of, realistic Boston scenarios for deliveries. And then I introduced a couple of routing heuristics, right? Where if you wanted to do this without route enumeration, you could. So what are we working on right now? We're working on in trying to improve how realistic this model is, right? So you can imagine that packages aren't all the same sizes, right? Maybe one takes up, more or less space. So you have to think about its effects on capacity. The more important one, I think, is the second bullet, actually. So your ice cream orders may not be as privacy, you might not care about your privacy in that case compared to a pharmaceutical order, right? So perhaps we could actually group certain items together that have similar levels of risk, right? So this is more realism in terms of methodology. One huge limitation is that we assume a one-to-one mapping between a vendor and a customer, right? Which is not realistic, because here you have, a vendor, Amazon, delivering to thousands of customers, or you could also have a customer receiving items from multiple vendors, right? So we're working on extending this to the many-to-one, one-to-many, and many-to-many case. This second bullet is also really intriguing to me. So this second bullet asks the question, if I observe, let's say, a year's worth of these trajectories, can I learn something more from that year's worth of trajectories than just a single delivery snapshot, right? Which is everything that I've talked about today. It's just one single execution of a route. And in this one, I think I mentioned briefly this dynamic routing thing, which, to be honest, I don't think is as applicable for the drone case. The most realistic situation is Amazon waits for a certain batch size to come in, they route it, and then they deliver it, right? The drone, it's not gonna be like the drone is flying, the Amazon sends it in order, and then the drone like has to land, pick up the order, right? So probably not as interesting as the dynamic order case for like Uber Eats, right? That's definitely a situation where dynamic ordering might be more applicable. And then kind of the two main avenues of work that we're doing right now is, again, what you actually want. You want to be able to design a route with privacy instead of just being able to analyze a given route, right? So everything in this was post hoc, right? You give me a route, I give you the privacy, or you give me a brute enumeration of all the possible routes, and I spit you out all the privacy, and then you select which one you want. What you should actually say is, I want no individual customer to be harmed by more than one path, right? Give me the most efficient route that hits that one half privacy goal, right? So you're kind of taking a slice, a vertical slice, and you're trying to minimize that route on that vertical slice, right? So that's precisely the formulation of the vehicle routing problem, right? While the vanilla formulation is just minimize some cost, and where the cost is travel time or fuel cost or something. But we would like to extend the VRP to a private version, right? So we have some ideas, like, currently when you do VRPs, one of the ways to do it is through what's called like the Mtz formulation, and you do subtour eliminations, right? We have a hypothesis that some subtours could map to nice permutations on our vendors or our customers. So if we could actually keep one of those permutations, then you have a generic family of route where it's basically a complete route, but at some points there are subtours in there. So now you are searching not over the space of all of the possible routings, you're only searching over the space of just those subtours, right? Another question, which we've really been doing some more mixed methods and survey type work in is, do people actually care about privacy in this setting, right? So we deployed a survey, an online survey. I think we have about 4,000 responses right now, trying to basically use the survey results and using a multinomial logit discrete choice model type framework to see if we can extract a dollar amount that someone might be willing to pay for an increased privacy on their drone package delivery routes. Because in this case, if you give, okay, you say, okay, someone who wants privacy is willing to pay $2, I can now come back here and say the cost, right? So now I'm evaluating, if I don't do the most optimal BRP route and I do something less optimal, I have some cost here. If this cost is less than or equal to the profit I can gain from charging the customers $2, then I probably am okay sending it out on this privatized route. So really, it's trying to extract the valuation of privacy from real, hopefully real people taking this survey. So with that, I think that was my my presentation. So I definitely wanted to leave time for questions and discussion, but thank you for listening.
A couple of questions. So this when the drones system started to becoming popular, maybe like 10, 12 years ago, this delivery was actually a joke that they would, because in terms of the lift, force and the energy that's required, you need it's like a quadratic relationship to the amount of power. So drones are actually fundamentally incompatible with actually lifting heavy loads. You see most drones out there, they'll have to have a really huge wingspan to lift anything above 10 kgs or something like that, right? So it's it's a case study, it's an example of, but so let me take a step back, right? So when we have this last mile delivery via the road with your Amazons and your DoorDashes and all of that, we don't have this problem, right?
Yes,
Why?
right. Yeah, that's a good question. So I think it's because right now, you're not tracking a Uber Eats' car, right? Or at least there's not a mandated identification procedure, right?
Right. So let's say, like, for example, so I mean here, the tracking is like every second, right? I think.
So they're still working on that. Like I don't think they've decided.
Every second, I think, when I mean, it's like the flight tracker, right? So
Right.
flight tracker is they have some kind of thing, but
The difference
yeah, just give me one. I just have a stream of questions.
Mhm.
Okay. So I think there's this load, load carrying
Mhm.
drones. The physics are against it.
Yes.
Fundamentally. So it can be used as an example, but the other thing is that these drones are like kind of delivering anything. They would not necessarily in an urban area. They might deliver it in a collection point, like an Amazon or whatever, the pickup location, and that takes care of the the randomization or the privacy.
Correct.
Or disaggregation.
Mhm.
So I mean, like, this is a problem that is like, it's a disaggregation problem. Like, it's
Yes.
a class of I mean, people look at that in terms of disaggregation of signals in a building. You turn on different appliances, but you only observe at one location. Can you identify which appliance? That was from actually MIT 76.
Mhm.
Like, so then in this case, if you're going to just a collection point, then that takes care of the privacy aspects, right? Because they just have a landing zone, and I'm just saying practically that would.
Yes, so I agree that if you
like
have
almost last mile.
yes, so if you go to some Amazon locker type thing,
Yeah.
right? So then you could still consider privacy now as a function of the population that is serviced by that locker, right? So but I agree that this is probably more applicable to the whole suburban case, right?
Right.
Where you're delivering to like someone's front lawn.
Yeah, because then there are other cases of where privacy matters, in terms of knowing the timing and the route.
That
Mhm.
means, I want to know when and which route you chose. So for example, if we just take the route,
Mhm.
Amazon, and this was a problem we were working on with Yash with before we had like a centralized routing
Yeah.
for all vendors.
Mhm.
Then we had to follow on with just, decentralized or actually distributed routing on a vendor by vendor basis. So then the route itself is secret.
Right.
But with the, say, like a low resolution monitoring, right? So you don't know the exact route, you just know, you can kind of try to reconstruct it afterwards.
Yes.
But then, like, say, for example, you have like a cash collection, like this Garda or these,
Mhm.
these cash trucks that pick up cash from retail stores,
Mhm.
right? So they want to, so their privacy issue is that they don't want to have a predictable route. And then they
Yes.
don't also want to stay in one place for too long.
That's right.
And so they want to kind of randomize the route every time. And then it's kind of going back to your last problem of, okay, if I look at a pattern over a year,
Longitudinal
yeah,
privacy.
yeah.
Yeah,
So
exactly.
Can I sort of get past that, right? And then a variation would be like, actually one of the problems that Shiva is working on now is opacity in terms of you don't know when you're going to get to a particular place, that you're keeping that secret.
Hmm.
So there are, many choice of routes, and there's kind of non-determinism in how the system will actually roll out.
I see.
And so that's kind of like in a war scenario. You don't want to reveal, what the exact path is, and you don't want to. They can always track you. They can always identify your location, but they don't know when you will actually reach the destination.
Right.
Because they have limited resources to deploy to figure out, are you going to go here, are you going to go here, and then they're just going to be ready and ambush.
Right.
But they can't do that, right? So I think there are all these variations that,
Yes. Absolutely.
like, so I think in terms of masking the route, masking the timing
Yes.
of the route. And then the last part I was thinking of was that most of these logistics systems have like what's called like a crosstalk.
Yeah.
And so the crosstalk is also kind of like a aggregation, disaggregation sort of place, which basically again introduces a lot of randomness into the delivery system, and then you can't. It's very difficult to disaggregate
That's right.
which packages came in and went, because it's one point. So it's a combination of the crosstalk and these Amazon lockers might structurally take care of this problem in an urban situation.
Yes, I agree. So I think this for the business case, it's more for people who wanted to lease out to a drone fleet operator and do door-to-door type deliveries, right? Certainly crosstalks as well as aggregate collection points are all privacy enhancing in some sense, right? Yeah, absolutely.
Yeah.
Yeah, I lost my thought.
Maybe you can describe your thing to Max. But just speak up. And if people online have any questions,
Oh yeah. I have not been monitoring, but
That's fine.
That may have been the danger.
No, that was good.
Oh.
Yeah. So sure, you can just explain now.
it's me. Finally, yeah.
Yeah, that's a little bit.
Yes.